Okay, in this section, we're going to be combining functions. Now, problem number 9 gives us two functions, the function f and the function g. And then parts A, B, C, and D tell us to do the simple operations of adding them, subtracting them, multiplying them, and dividing them. So let's get started with adding them. When we add two functions, we simply do just that. We add them. So f of x plus g of x could be written as f plus g of x. It means the same thing. So I'm just going to replace f of x with 2x squared minus 5. And then g of x is equal to x plus 4. Now, I can take these out of their parentheses. And I can look for like terms. And I see that I have a minus 5 and a plus 4. So that will give me a minus 1. So I'll have 2x squared plus x minus 1. Part B asks me to subtract the two functions. So we know that f minus g of x is the same thing as saying f of x minus g of x. Notice it's very important to keep them in the order they're listed in. So I'll write my f of x as 2x squared minus 5 and my g of x as x plus 4. Now, when you're subtracting, you have to be very careful. Throughout this semester, whenever you're subtracting two polynomials, you have to remember that you're going to need to distribute the minus. Now I'm going to look for like terms, and this time I have a minus 5 and a minus 4, so that's going to be minus 9. So I'll have 2x squared minus x minus 9. Okay, oh, we forgot. We're also supposed to state the domain. Now the domain, these are my allowable x values, my inputs. Okay, so when we combine these functions, we have to realize that the domain of the combined functions is the intersection of the domains of each. So what I'm going to do is I'm going to consider what is the domain of f of x. Well, the domain of f of x, it's a parabola, so we know the domain is negative infinity to positive infinity. And the domain of g of x, well, that's a linear equation, so our domain is negative infinity to positive infinity. The domain of our combination, so of A and of B, is where these intersect. What is in both of these domains? And you can see that both of the domains have negative infinity to positive infinity. So when you're looking for the domain, look at each one separately and then ask yourself, what do they both have? What are the x values that they both allow? And that will be the domain of your combined function. Let's move on to part C. Part C says the function f times g. So we can write this like this, or we can say that's going to be f of x times g of x. So I'm going to write their equivalent values. And you can do this whatever method you like, distribution, box, FOIL, whatever you feel comfortable doing. I'm going to say this is 2x cubed plus 8x squared minus 5x minus 20. So this is the product of function f and the product in g. Now, it also asks us for the domain of this. And once again, our domain will be the intersection of the domain of both of the functions. So it'll be negative infinity to positive infinity. Now, part D. This is division of these two functions. So I can write it like this. I can say f of x divided by g of x. And I can just fill them in. Now I could try to factor the numerator and I'd see that it doesn't factor. So this is simplified. So this is our answer. Now I wanted to point out though that the domain of a division of a quotient problem where the functions are divided, we have to consider one more thing. So we consider the domains like we did earlier. We consider the domain of f of x and the domain of g of x, and we see what they have in common. But we also have to consider the denominator. Now we know that a rational expression can never have a denominator that is equal to 0. So we never want our denominator to equal 0. So we know that for this problem, when x is equal to -4, we'd have a problem, right? We'll have division by 0. So we don't want to allow division by 0, so we'll exclude -4 from our domain. So our domain is not going to be -infinity to +infinity like it will be for addition, subtraction, and multiplication. Instead, we're going to eliminate -4. So we'll say -infinity to -4, in union with -4 to infinity. And that will eliminate that -4 so that we don't create division by 0. So on these problems, when they ask you for a domain, the one that you have to be extra careful on is division. I'm going to put on here, division. Be careful with the domain. You don't want to allow division by 0. Okay, let's try problem 11. Very similar to the last problem. Part A asks us to add the two functions. So we know that when I add the functions f plus g, I just literally add them. So I'm going to say 4x cubed minus 5 plus 2x plus 7. And I can add them directly. I can just take them straight out of their parentheses and look for like terms. So I have 4x cubed, and I have a minus 5 and a plus 7. That's going to be plus 2. So I'll have 4x cubed plus 2x plus 2. Now, for our domain, we have to consider the two functions. Our domain of f of x, this is a cubic. So we know our domain is going to be a cube function has -infinity to +infinity as its domain. Our g of x function is a linear function. So it also has a domain of -infinity to +infinity. Therefore, our domain of our combination, adding, subtracting, or multiplying, will be -infinity to +infinity. That's where they overlap. Let's look at part B. Part B asks us to subtract the two functions. So all I need to do is subtract them. Now notice I put them in parentheses to remind myself that I need to distribute that minus. That's the gotcha on these problems. I need to distribute that. So in my notes, I would put something like, warning, when you subtract, you must distribute the negative. And then we're going to look for like terms. So I have a -5 and a -7. I'm going to say that's -12 or -12. So I have 4x cubed minus 2x minus 12. And our domain, once again, is just going to be -infinity to +infinity. So your domain will be the same for addition, subtraction, and multiplication. Part C asks us to multiply the two functions. So we're strictly going to multiply them. Function f of x and function g of x. So I'm going to get 8x to the fourth plus 28x cubed minus 10x minus 35. And I look for any like terms, which there are none. And once again, our domain is the same, addition, subtraction, or multiplication, once we've discovered it. But for division, it's different. So warning, division, you're going to be careful on. When I want to divide the functions f by g, then I'm going to put my f in my numerator and my g in my denominator. I can try to simplify this by factoring, but it won't factor. So this is my answer. Now my domain, it's no longer just going to be negative infinity to positive infinity. Instead, I have to consider this denominator. I don't want my denominator to equal 0. So I say to myself, when will it equal 0? What x values will cause it to equal 0? And I can see that x cannot equal negative 7/2. If it does, then I'll have to division by 0. So therefore, my domain is not negative infinity to positive infinity. I'm going to exclude negative 7/2. And I can write it like this to make sure that it excludes negative 7/2. Okay, so let's look at a couple of these composition of functions problems. So be aware that this is very different than the last problem. In the last problem, we had a closed circle between the two functions, and this means multiply. Now we have this open circle, and this means composed with. Another way you can think of writing this is you say f composed with g of x. So this second function is now the input for the first function. It's a chain reaction. So let's look at part A. Part A says f composed with g, which we could write as f and then put g of x in the input. So the way I start this is I replace g of x with its value. We know that g of x is equal to x squared minus 2. So I could write f composed with g as f of x squared minus 2. Now I write the function f of x, and then I consider when x instead is x squared minus 2. So I'm going to replace, everywhere there's an x, I'm going to replace it with x squared minus 2. That's my new input. And I'll distribute this out. So the function f of x squared minus 2 will be 9x squared plus 20. Oh, I think I made a mistake here. Let's fix that. Should have distributed that and made it a minus. So it's going to be 9x squared minus 16. That looks better. Now, it also asks us to state the domain for each composite function. So our composite function is 9x squared minus 16, which we know the domain of this function by itself would be a parabola, so it's going to be negative infinity to positive infinity. But we have to be respectful of the domain of the input, so we have to consider that. So the domain of g of x, well, it's a parabola also, so its domain is also negative infinity to infinity. So our domain will be negative infinity to positive infinity. But if g had some restrictions, we'd have to make sure they're also implied in the restrictions for the composition of the functions. Let's do another one. Let's do b. b is g composed with f. We can write it like this. Sometimes this helps me see it when I write it like that, because then I see that this is simply g, and instead of the input of x, it's going to be f of x, which is 9x plus 2. Now, I'm going to write the g of x function, which is x squared minus 2. And now I'm going to write g at 9x plus 2, because that's what we want to find out for this composition of functions. So I'm going to write the g function, but everywhere there was an x, I'm going to replace it with 9x plus 2. And now I'm going to multiply this out. I'm going to look for like terms. And I'm going to get the function g composed with f is equal to 81x squared plus 36x plus 2. I have to state the domain for each function, for this composite function, sorry. Okay, now the domain for the composite function, if I look at this 81x squared plus 36x plus 2, this is a parabola, it's a quadratic. So we know its domain will be negative infinity to positive infinity. But with compositions of function, we have to be respectful of that inputs function. So f, our function f is 9x plus 2, and its domain is also negative infinity to positive infinity. So we don't have to make any additional restrictions. So our domain is negative infinity to positive infinity. All right, let's try part C. Now we're looking for h composed with f. We could write this as h, and then put the f of x as our input. So I could write this as h, and then instead of my input, I'll put my output of f of x. So 9x plus 2. So I write h of x is equal to 4 over x plus 3. I don't want that. I want h at 9x plus 2. So wherever there's an x, I'm going to replace it with 9x plus 2. And then I'm going to multiply this out, and I'm going to get 9x plus 5. So this is our composition of functions, h composed with f. Now, it also asks us for the domain. So we have to say, what is the domain of h composed with f? Well, we know there's a rational function. And rational functions, you have to be careful not to let the denominator equal 0. So we can never let 9x plus 5 equal 0. We never want the denominator to equal 0. This would cause our function to be undefined. So I'm going to look for the values for x that will cause this to happen by setting the denominator equal to 0 and solving. So I can see that I do not want x to ever be allowed to equal negative 5/9. So my domain for this, for the composition function would be negative infinity to negative 5/9, and I'm going to exclude it by putting parentheses on each side of it. And then in union with negative 5/9 to infinity. I'm not done yet though. I have to also check my inputs domain. I have to be respectful of that. Now my input is 9x plus 2. So the domain of the input is negative infinity to positive infinity. It didn't have any restrictions. So I don't have to add any restrictions into my domain. So I am done. But if I did have a restriction, I would add it into my domain. One more, let's try part D. So this is f composed with h. You could write it like this. If this makes more sense to you, you can see that h is the input for f. And that means that we can write it like this too. We could say f, and our input now will be h of x, which is 4 over x plus 3. Okay, so now let's just write, what is f of x? Well, f of x is 9x plus 2. That's given. So then f of 4x plus 3, wherever there's an x, instead I'm going to write 4 over x plus 3. So I'm going to get 36 over x plus 3 plus 2. This is what f composed with h is. Now I want to get a common denominator, so I'm going to multiply. Let's go ahead and multiply 2 times x plus 3 over x plus 3. And I can do that because x plus 3 over x plus 3 is the same thing as 1. So I'm going to get 36 plus 2x plus 6 over x plus 3. And all I did was distribute this if you're confused about that, which would be 42 plus 2x over x plus 3. So this is f composed with h. Now it wants us to state the domain. So first let's look at what is the domain of this function we just created, this f of h. Well, like in the last problem, we have to be respectful of the domain because we never want division by 0. So we have to restrict our domain. And the way we do that is we say x plus 3 can never equal 0. So we want to find out what values will create that. And we'll set it equal to 0 and solve. So we never want x to be negative 3. So our domain would be negative infinity to negative 3. And then we're going to exclude it by putting parentheses on each side of it. Okay, but we're not done. We have to always look at the domain of our input. Well, our input is h of x. And you can see that h of x also will have the restriction of not allowing negative 3. That's the same restriction we already have, so we're good. So our domain for our composition of function will be the same. Our next problem asks us once again to find those composition functions, okay? Composite function of A will be, it says f composed with g. We can rewrite it like this if it makes more sense to us. Okay, the function g of x is now the input for f. So I like to rewrite it like this. I put, instead of g of x, I write what g of x is equal to, negative 6x squared plus 10. So now I'm going to look at the function f. Well, f of x was 8x minus 9. But now I want f at negative 6x squared plus 10. So wherever there was an x, I'm going to replace it with negative 6x squared plus 10. And I'm going to just simplify this by distributing it. And I can look for like terms, and I'll get negative 48x squared plus 71. So this is our composite function. Now, we want to find the domain. So we first start by saying, what would be the domain of this composite function, just the way it looks at it? This is a parabola, so we know our domain is negative infinity to positive infinity. But we have to check and be respectful of the input's domain. And our input is g of x, which is negative 6x squared plus 10. The domain of this is also negative infinity to positive infinity, so we're okay. We don't need to add any restrictions. Let's try the next part. So for part B, we want g composed with f, which we could write like this. I like to replace f of x with its value, which is 8x minus 9. Now we know that g of x is equal to negative 6x squared plus 10. So g of 8x minus 9 would mean that everywhere there's an x, we're going to replace it with 8x minus 9. So let's expand this out. And you can see that g composed with f will give me negative 384x squared minus 864x minus 476. Now, to find the domain, I look at my composite function. It's a parabola. And I know that the domain of a parabola will be negative infinity to positive infinity. But I want to check before I say that's my answer. What is my input of, what is my domain of my input function? My input function is f of x, and it's a linear function, 8x minus 9, which also has a domain of negative infinity to positive infinity, so I don't need to add any restrictions. Let's keep going. Let's look at part C. This is h composed with f. So we can write it like this. The input for h will now be the output of f. So I write the function h, and in place of f of x, I write what it's equal to, 8x minus 9. Okay? Now I look what h of x is equal to. It's equal to the square root of 2x plus 11. So I'm going to replace x with 8x minus 9, because that's the input I want to look at. And everywhere there's an x, I'm going to write 8x minus 9. So this is going to be 16x minus 18, I'm just distributing, plus 11. And I get h at x, 8x minus 9 is equal to the square root of 16x minus 7. That's what our composite function will be equal to. Now, It also asks us for the domain. So looking at our composite function, we have to ask ourselves, do we have any restrictions? Well, we do. Whenever we have a radical, we know that the radicand, the stuff under the radical, so 16x minus 7, has to be greater than or equal to 0. Okay? So we're going to add 7 to both sides and then divide by 16. And I'll see that x has to be greater than or equal to 7/16. So my domain of this composite has to be greater than 7/16 or equal to 7/16. And you could write it like that, or you could write it in an interval notation, and we would know that would be 7/16. So we needed a bracket since I got an equal, greater than or equal to infinity. And I would accept either one. Now, we also have to check the domain of the input function, which was f. And our domain of our input function would be negative infinity to positive infinity, so it doesn't have any additional restrictions. This is restricted enough. So this is our domain of our composite function. And let's do part D, f composed with h. So I'm going to replace h of x with the square root of 2x plus 11. Now, f of x is 8x minus 9. That was given. So we're going to try f of the square root of 2x plus 11. Everywhere there's an x now, I'm going to replace it with the square root of 2x plus 11. And we can't simplify this, so we're just going to leave it as 8 times the square root of 2x plus 11 minus 9. So this is f composed with h. Now the domain, we want to look at our composition, our composite function. We can see now that in our composite function, we have a radical. So we want the radicand, that 2x plus 11, to be greater than or equal to 0. So let's just go ahead and solve for that. So we'll say that x has to be greater than or equal to negative 11 halves. That's going to be our domain for our composite function. Now we're going to also be respectful, though, of our input, which in this case was h. Okay? So our input function also has a domain restriction of it has to be greater than or equal to negative 11 halves. So our domain of our composite function will be x is greater than or equal to negative 11 halves, or if you wanted to, you could write it as negative 11 halves to infinity if you wanted to use interval notation. Okay, number 29. So number 29, we're just simply adding, subtracting, multiplying, and dividing the two functions. So A asks us to add them. We know when we add functions, we can separate them out. Oops. And say this is f at negative 6 plus g at negative 6. That's the same thing as saying f plus g at negative 6. So I'm just going to evaluate f at negative 6. So in place of x, I'm going to write negative 6. And now I'm going to evaluate g at negative 6. So everywhere there is an x, I'm going to replace it with a negative 6. So when I now can replace f at negative 6, I'm going to write negative 85. And g at negative 6, I'm going to write 58. And when I subtract those two, I get negative 27. Let's move on to b. So b, we're going to do the exact same thing. This time, though, we're saying it's going to be, we're evaluating it at negative 4, not negative 6. So it's going to be f at negative 4 minus g at negative 4. So I can evaluate what is f at negative 4, and then what is g at negative 4. So I replace every x with a negative 4. Get f at negative 4 is negative 43. Now let's do g at negative 4. So I'm going to take my function g of x, and I'm going to replace x with negative 4. And I get g of negative 4 is 42, so I'm going to replace g at negative 4 with 42. So negative 43 minus 42 is going to be negative 85. Let's try part C. Here we're multiplying, and we know this is the same thing as saying f at 1 times G at 1. Okay, so let's evaluate F at 1. And we get -8. And I evaluated G at 1 and we get 2. So we can replace F at 1 with -8 and G of 1 at 2. And so -8 times 2 will be -16. And then G asks us to combine F and G with division. So what is the quotient of the F divided by G at 7? And we know we could write it out as F at X divided by G of, we could write it as F of 7 divided by G of 7. So let's evaluate what is F at 7 and what is G at 7. So I found that F of 7 is -98 and G of 7 is -46. And if I simplify that, I'll get 49/3. Okay, the next one is a word problem. So I'm going to give you a moment to read it. So pause the video and read it yourself. So when you're doing a word problem, we know that there's 3 steps. The first one is understand the problem. So we can see that they gave us a function that is first revenue, right? So this first function is revenue, where X is the number of refurbished cell phones sold, okay? And then they gave us total cost. They said it was $450 plus a variable cost of $20 per cell phone. Okay, so I can kind of get the idea. Now, write the total cost function C of X for this problem. So it told us that the total cost is going to be $450 plus a variable cost of $20 per cell phone, where X is the number of cell phones. So this is our cost function. Now our profit function, we have to realize that profit is always revenue minus cost. This is just a business model that if we're selling something, how much did it cost us to produce it? You have to subtract it off to how much money you brought in, okay? Revenue is the amount of money you're bringing in. C is the amount of money you spent. So in our case, the revenue function was given to us. And the cost function we just made ourselves. So we're going to subtract the revenue function minus this cost function. Notice I'm very careful to put them in parentheses whenever I'm using a subtraction, because I'm going to have to distribute that minus. So I'm subtracting the 2 functions. Okay. Now when I do this, be very careful. Look for like terms. I can see there's an 80x and a minus 20x. So I combined those and got 60x. So our profit function will be this. Okay, and then it asks us in C to find and interpret P at 50. So we know we're just going to evaluate our function at 50. You can use your calculator to get $2,525. And then last, it asks us to interpret that. So just go back and look and see what the input means. Well, in this case, the input is X, and X means the number of refurbished cell phones. So this tells us that if we sell 50 refurbished cell phones, we can expect a profit of $2,525. That's wrong here. Refurbished. That's better. So let's read our next problem. It's about a computer store, and it's having a sale. We all love to shop, so these are really important. These composite functions, they really help us figure out the best deal. So we can get a rebate of $50 and a 10% discount. And P is the dollars for the suggested retail cost of computers. Part A asks us to write a function that represents the laptop's cost after the rebate. So this will simply be P minus 50. Part B says, wait, let's just now consider only after the discount. So this is going to be 0.9 times P. A 10% discount means we're going to pay 90%, so 0.9 times P. Part C asks us to interpret R composed with D at P, which we could write as R and then put the D of P as our input. So we know R of P is equal to P minus 50. So R of D of P, we can replace D of P with 0.9 of P. So R composed with D will be 0.9 P minus 50. And it asks us what this means. And this means that our laptop was discounted 10%, and then we got a rebate. Let's look at D. D says, find and interpret now R composed with D at 650. So we can take our function we did in C and just evaluate it for 650. And we will get 535 is the price after the discount followed by a rebate. So you have to look and see which one came first. Well, the input was a discount, right? And then we get a rebate. All right, now let's look at E. Now for E, we ask D composed with R. So you can see it's a chain reaction. In this one, the rebate is first, okay? So we can write this like this, if this makes more sense to us, okay? So R sub P, we said that D sub P was 0.9 P. So in place of P, I'm going to replace it with P minus 50. I'm going to get 0.9 P minus 45. Let's follow the reaction, the chain reaction. The input is going to be first with a rebate. And then we're going to follow it with our discount. Part F asks us to apply D composed with R at 650. So we're going to take our function we just found in part E, and we're going to replace P with 650. This would be the price, would be $540 if we get the rebate first. And then we get the discount. And then part G says, which composite is better? So we said that for part D, our price was $535. And in part F, our price was $540. So we can see that R composed with D is a better value because $535 is less than $540. So I want to have the 10% discount off the regular price first, and then I'll get a better deal. The next column is not a composition. Instead, it's decomposition. So we're going to basically take the function apart. So we're given function h, and we want to break it down into an f and a g. But h is made up of f composed of g. Okay? So an easy way to look at these problems is see if anything's repeating or if there's a function that you could take out the whole thing. So for example, I could let g of x equal 7x squared minus 4. Okay? And then I could write f of x is equal to negative 2, and I will just put x, because we know that I'm going to put this g of x in for x. So my two functions would be f of x is equal to negative 2 times the absolute value of x, and g of x is equal to 7x squared minus 4. Let's just go ahead and check and make sure that f composed with g will be equal to our original h function. So for f, I'm going to write negative 2, and in place of x, I'm going to put g of x. And I do get h of x. Now, there are more than one answers. There's more than one answer for these. You can try different combinations. So do not think that you only have one way to do this. Let's try another one. Now, this one I can see that x minus 3 repeats. And I can see that it's going inside of parentheses. So let's try, what if we made g of x equal to x minus 3? And the reason I'm choosing g of x because I know that's going into f of x. So I can make f of x equal to x cubed plus 2x squared plus 1. Because everywhere we have f composed with g, what I'll do is I'll be putting in place of the x, I'll be putting the g. And you can see that will be what I get. And so this is one possibility.